Alright, so let's look again what we did. So solving this actually, solving this partial differential equation, although the derivative is only in x, it's still partial differential equation because the solution is in x and y. Okay, the solution is function of x and y. This is actually as if we solve it as if it was an ordinary differential equation and not partial differential equation. Alright? This is the way you treat an ordinary differential equation. But rather than a and b is function of y, just a and b is constant. Or you get them from the boundary condition. And you basically, if this was an ordinary differential equation, and we'll use this today, often and often, because I told you the trick is that we will turn our partial differential equation into two ordinary differential equations. And then we'll take the two ordinary differential equation and we'll solve each one of them along those same lines. Alright? So anyway, so this is what we did, right? And over here, that's the clean version of it. Okay, so he's basically saying that we are solving this as if it was ordinary differential equation, right? And here is another one. Rather than xx, now it's uxy equal minus ux. Alright, where u is u of x and y. So how we can solve this also along the same line? Well, he basically first he wanna turn it into just x and x like this one. You just want to see only x's so that he can write the solution in terms of e to the power x. So he just want to see one variable. So he will get rid of ux. He will call ux. What's ux again? It's partial u partial x. So by calling ux a new variable p, then this equation rather than being uxy, it becomes py. Right? And this, rather than minus ux, become minus p. And now this equation in this new variable, rather than u, now it's p, and it's kind of ordinary differential equation in y. Py equal minus p. So you bring, I'm just rewriting py as it's actually partial b partial y. And here is the b, bring it over here. You got partial b partial y over 1 over b minus 1. How you integrate this as ordinary differential equation? Well, you take the b under the partial p and this become y. So the solution is len p equal minus y plus a constant. That constant is not really a constant, it's a constant of x. The reason why it disappeared here, because you differentiate this with respect to y, this guy will be 0 because it's only function of x. So what I'm trying to say is that when you are integrating a partial differential equation of y, the constant should be function of x. Because when you differentiate this with respect to x, to y, anything that's function of x will disappear.
So is that py equals negative p?
So that's minus. This is len p, len.
Yes, that is a negative.
Minus y plus c1 of x. Alright, so c1 of x. So what we're gonna do next? What's the plan? The plan is we eventually would like to have p and y, so that we go back again and say that p is actually ux and we integrate this. So this form doesn't really help that it's summation. We wanna, so how we pull it into integration, and this len also is not nice. So he's basically saying, well, that c1 of x can also be len c2 of x. You know, any constant can be len of another constant. Okay, the reason why he's doing this is that then he'll take this len and that len, and len minus len is len p over c. Remember, len x over y is len x minus len y. Alright? Equal minus y. And so if this len those guys is minus y, that means that those guys is e to the power minus y. Or simply p is c2 e to the power minus y. Alright? So now back again, what is that p? That's partial u partial x. So partial u partial x is equal to those guys. You integrate with respect to x, and you'll end up with e to minus y. This doesn't really concern us when it comes to the integration with respect to x, because it's kind of constant. So we are just integrating the c2x dx, right? c2x dx, it's a function of x, right? We just get the function of x. And that when we are integrating this original one, you integrate this plus a constant. Again, that constant is not any constant, it should be function of y. Because when you differentiate this with respect to x, when you differentiate this equation, anything that's function of y will disappear, will become 0. So that's why when you back up, when you integrate, when you're trying to bring a constant, it should be constant of y. Right? So here is the final answer. It's function of x, function of y. E to minus y, function of x, plus function of y. And those guys, how we are going to get those guys? What is this function of x and what is that function of y exactly? How we will get the exact value? Exactly. When you hand me this equation, you just don't hand me the partial differential equation and tell me integrate. There is infinite number of solutions that can work. You need to also give me the boundary condition. The boundary condition for x and y. Right? So those boundary condition will be the one that will get the exact value of x and y. Alright? And so here is a clean version of the solution. Alright? He's explaining basically the steps that we just did. Alright. So here he will, because vibration is important for mechanical engineers, he will just shortly show us where did this come, where those partial differentiation come from. Okay? So you start with this, the vibration of a string basically, like all those instruments, when you pull the string and you let it vibrate and it will make all those music. And actually here's a picture. I guess they are shooting with, they had the exposure open, the camera is open for a long time, so that the wire shoot up multiple times. It's as if you are shooting a soccer player who's really fast, and his leg will end up showing many times, right? Tuck, 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 and just because it's like so quickly. So the same thing for the wire, except look at this point. Why this point doesn't seem to move at all? It's a node. It's a point that doesn't move. So that wire, that string can actually vibrate like this, or can vibrate like this, or can vibrate like this. Those are called the harmonics of the vibration. The equation of the wire, what are we trying to solve? It's the U. It's basically how the displacement of that wire. So when you move up and down, we basically assume that every point just go up or down. They don't go right and left. The wire just basically, okay? So really the function, the unknown is the U of x and t. U at every x, which is the length of the wire, and also as function of t. We want to track it as function of time. Will it keep vibrating forever? Will it vibrate and eventually die? And where will it vibrate? Will it vibrate like this or this or this? So the solution will be U of x and t. And that's the equation, the wave equation. And he will prove to us why it's like this in a second. It's second order in t and second order in x. Alright? And why he got c squared? I mean, that's a constant that he could make. Just see why it's c squared. What does he want? Why is c squared, not just c or k or m or n? Because he mean it is, it's positive. It's positive. That's his way of insisting it should be a plus 5, plus 7, by saying it's c squared. So whatever the c is, whether you want to pick c 7 or minus 5 or 5 or plus 5, the c squared will always be constant. Right? So you want to say it's constant. Sorry, it's positive. So why this is the 1D wave equation describing all those modes, and which one will really work, we'll find out. So the assumption is the string per unit length, the mass of the string per unit length is constant. He's basically saying a uniform wire, of course, I mean if it's heavier in one part than the other, it wouldn't really make those sinusoidal. Alright? And it's basically the tension is so much compared to the gravity, forget that he will, if you are not really leaving him by itself, it will slack down. There is no such thing. He's under tension and gravity is not there, or very little, or it's as if basically he's, in microgravity or something. Alright? Very good. And he's saying basically that she just move up and down. So how you are suggesting, before you look, don't look at the solution in front of you, how you think we can get this equation? Yes.
Combining the frequency equation.
I don't know what's the frequency equation. What do you mean the frequency equation? how we can no, you actually, that remind me when I was a senior, and one of our professor asked us this question, and we all like, huh? And he basically shouted at us, and he said, you know, why do you always imagine there is still black boxes that you don't know? You already, by now, you know all the equation that's available. It's done. You know the equations. It's all just combining different equation to come up with the solution for different problem. So I'm telling you, you know the equation that will give us this. Huh? I'm not asking about the solution to solve this. I'm saying how we can prove that this is the equation. If the problem is this, your boss told you we had this wire and we figure out that if you pull it, it keep moving up and down. We want to find out what is the equation.
Would it be the momentum equation?
Excellent. And for a solid, it's not fluid. This is just a solid wire. The momentum equation for a solid, it's called, what do you call that equation that describes the momentum of a ball or a sphere or my iPhone if I threw it?
Momentum of a solid equation?
Yeah, what is the name of that? Newton's second law.
Oh.
It describes the momentum of something, huh, due to a force. If you put a force on it, he will change his linear momentum, right? So I probably need to take a mass, a little bit of a mass over here, huh, and write the forces on it. Put the forces and tell myself that the force is equal to, what's Newton's second law? Force equal to mass time acceleration, right? M dv by dt. dv by dt, that's basically, he's moving up and down, so it's really d, if u is the position, so the velocity become du by dt, and therefore the velocity is du by dt, so the acceleration become d2u by dt squared. You already put your hand on why there is a second derivative in the time, right? So that's what will happen exactly. So, ouch. So here is the piece of wire. He's making a piece of the string. Alright? Mass, probably density per unit length times the length of this mass. Rho is the density per unit length times delta x. That's the mass. Alright? And the momentum equation can be written in x direction and y direction. You can put the forces in the x direction, you can put the forces in the y direction. Right? So what are the forces? We said no gravity, or gravity is very little. So no gravity. Then what other forces are there? What are those? Tension. And so the tension of the wire is always more than constant. It's always in the direction of the wire. So the wire cannot pull you in different direction. I mean, the wire cannot. Where is the wire? So I mean, this wire, you know, if it's bent like this, he cannot pull you normal to it, right? It has to pull you in the direction of the wire. Like you know, those old wheels when they were like basically on spikes, they always carry tension, right, in their direction. Or your wheel, the bike wires, they only carry tension along them. So he's basically saying there is a certain curvature here with two different angles. The tangent is alpha, tangent here is beta. I mean, it doesn't have to be symmetric all the time. And the tension is T, and the tension is T1 and T2. Alright? And so in the x direction, in the horizontal direction, since he's not planning to move to this way or that way, there must be no acceleration in the x direction. Therefore, the forces in the x direction should be basically balanced. Right? Otherwise, the wire will end up going like this. And so what are the forces? T2 cosine beta, the slope here. T1 cosine alpha, the slope over here. Those must be constant. And let's call it T. So T is basically the tension in the horizontal direction. Alright? And in the vertical direction, well, actually there is a motion. It's because there is not really a balance in the vertical direction. That's why he keep moving up and down. Right? So there could be a net force in the upward direction. And so it's, what is the vertical direction then? It will be T2 sine and T1 sine. So T2 sine beta minus T1 sine alpha equal to mass time the acceleration. Again, the position is u, the velocity is partial u partial t, therefore the acceleration is partial t u partial t squared. Alright? So now this T2 and T1, you already know that T2 can be represented by the T over cosine beta, right? And T1 can be represented by T1 cosine alpha. Or another way to think about it is we can basically divide the whole thing by T. Divide the whole equation by T. Either way, whether you are cancelling T1 in favor of the T cosine alpha and T cosine beta, or whether you are dividing the whole equation by T, you will end up with this. And the mass, that's rho delta x. Ouch. So basically what you will end up over here is sine beta over cosine beta, which is tan beta, minus sine alpha over cosine alpha, that's tan alpha, equal to mass time second order derivative. What is the slope of that thing? Sine beta. That's the tangent to the line. The tangent of the line is actually partial u partial x. If this is u at a certain moment in time, that's the displacement. The wire in this, or the string at that time, is basically he's attached at the 2 points, but at different location he has different u. That's u as function of x during this moment. Next moment he will go up or go down, but the point is that slope is partial u partial x. So if this is at x and this is x plus delta x, this become partial u partial x at that point, and this become partial u partial x at that point. You take that delta x and you divide it under those guys, it become like this. And we are supposed to do this so that it actually be accurate. It's supposed to be for a very small delta x, so small that delta x go to 0. Then this become the second derivative, because it's basically the change in the first derivative over a very small distance. It's the rate of change of the first derivative. Hence the second derivative, rho over t partial 2u partial t squared. Rho over t, that's always plus density, tension. It cannot be under compression, right? Doesn't work. You will buckle. I mean, you will get squeezed. So this is always plus. So let's call it not just c, let's call it c squared. It's a constant where c squared is rho over t, and that is 1D wave equation. Right? So all those partial differential equations, they come just from, you know, conduction, Fourier law. We will write it today, hopefully. Or basically just Newton's second law. They will all eventually generate those second order differential equations. Right? So that's why we are stuck with those, and we have to learn how to solve them. That's the way things are run in nature. Very good. So let's solve this equation, and we'll solve it by separation of variables, and then by Fourier. That's why we have been interested in Fourier series. So here is the equation we are trying to solve, and the c square, that's the constant we talked about, u over rho. And now to actually solve it, we need the boundary condition and initial condition. Boundary condition, that's at t whatever but x equals 0, and at t whatever and x equal L. That's the two ends of the wire. Are you holding them straight at 0, or you are basically shifting one of them, or right? I mean, you could shift one of them higher than the other one. This guy is like 1 centimeter higher, and you are basically moving it like this or something. So anyway, those are the two initial boundary condition, and the initial condition will end up being at t equals 0, u of x. So at every point on the wire, initially when we started the clock, when the problem started, where was the wire? Did you pull him to be rectangular, for example, triangular? Or did you pull it from 2 points? Or did you pull 1 point from the top and the other point to the bottom, and then you released? So those will affect the way he will start vibrating. Right? Robert, you had a question.
In the equation in here, it was density over time, and then it switched to time over density. How did we do
It's
that?
not time, it's tension.
Okay, tension. Now what's just above it? It's density over tension.
Well, look at this. This is T is here and now T is there.
Okay.
So it's flipped on the other side, right?
Gotcha.
Right. And by the way, so the nature of this constant, that's not the job of this course. This course start here, right? This course start here. This is basically the system, fluid mechanics, heat transfer. They will feed us those equations. It's nice to know where they come from, because we are not in math department. We are mechanical engineer. You know, we need to know why we are solving this equation. When I was a student, my struggle was they handed us this without even the c squared. They give us this equals 7 this. What? I mean, what is that exactly? Where did this come from? So I make a point that I would like you to see where those come from. But however, you shouldn't be worried about this part. All right? Shouldn't be worried about this part in the solution. All right. So we got bunch of initial condition. Sorry, bunch of boundary condition and initial condition. And notice that the initial condition could be u of x and 0 or ut of x and 0, the gradient. Okay, because it's second order, you actually need then two. You need this and you need this. All right. If this was partial u partial t, this would work. But if it's partial 2u partial t square, you need this and this. All right. Same thing here, partial 2u partial x square, you need this and this. All right. So this method separating variable, he will try to turn the ux of t into two separate functions. One of them just of x and the other one is just for t. And the u, the solution of that wire or string vibrating, is basically those two functions multiplied by each other. This will help the math a lot of solving this. This is not supposed to be easy. You're supposed to hit this so that when we go to chapter 21, you say, wow, that's super nice. We should keep using numerical methods, right? But again, if we can do it analytically, you know, with a little bit of math, that's of course always better than an approximate numerical method. No matter how good the approximation is, it remains approximation. All right? So we will have to learn also how to do this. So here is the trick again. U is f of x times g of t. Function only of x times function only of t. All right? So now, if it's like this, partial 2u partial t squared, that means you are differentiating this partial t twice. So when you differentiate this with respect to t, f of x is just a constant. It's like a 5 or a 7. It doesn't matter that it's sine x or e to power x, or right? When it comes to the differentiation, this guy will remain f. It's this guy that will differentiate once and twice with respect to t. So he make it with this g double dot. So dot mean partial u partial t, or partial g partial t. But since g is only function of t, differentiating it with respect to t is like a total derivative. That's the only thing that it's function of. And the same thing here, if you differentiate this with respect to x, g is a constant because it's only function of t, it remains as if it's a constant, and this become f double prime. So it's like df, d2f by dx squared. Okay, it's like the total derivative for f with respect to x. All right. So now let's plug this and this into this, the mother equation, which was what? Second derivative of t, c squared, second derivative of x. Second derivative of t, which is f g double prime, c squared, second derivative of t, of x, sorry, f double prime g. So, and in the next step you realize why he went through all this trouble, because now he can send all the g on one side, all the f on the other side. All the stuff that's function of x on one side, all the stuff that's function of t on the other side. You get this? Where did this come from? Right? This, you're looking at partial 2u partial t squared. And this is partial 2u partial x squared, and there is c squared next to it. That was the equation. Partial 2u partial t squared equals c squared partial 2u partial x squared. So now he will do this, okay? He will move all the g's together. You will get g double prime, sorry, g double dot over g, and here f double prime over f. F double prime over f, g double prime over g, the c square doesn't matter, you put it any way you want. But look at this. Function of t only equal to function of x only. So no matter where is the x, whether x is 0 or L, no matter what is the t, this always holds. So for any t and any x, this left hand side will be always equal to that right hand side. How is that possible? No, it must be that they are constant. This left hand side and the right hand side is not really x or t. It must be 5 or 7 or minus 3. That's the only way this side, no matter how much is the x and how much is the y, sorry, how much is the x and how much is the t, they always equal to each other. So it's a constant k. Alright? And so here's the genius of that step. So when we did this, using this, now we can separate the variable by saying, so this equal to this equal to k, or basically this equal to k and this equal to k. So by solving this by itself, f double prime over f equal k, here it is, that's an ordinary differential equation. This equation is only function of x, excellent. And this equation is only function of t. Alright? So you solve the wave equation using the separation of variables step. Will this always work for any partial differential equation? No. Well, that's why we had the numerical methods, in case that it's not really, cannot do that sometimes. Alright? So now how we solve this? We already did, remember? We solved this before. If I go back here. What about this? Wasn't this uxx minus u? That's the same idea, huh? But it was 0, it wasn't k. So maybe the solution, I mean, it should be the same line, but maybe it's not exactly like that. We'll see in a second. So we are solving this, okay? Here's the equation we are solving. F is only function of x, this is only function of t, alright? And when we get this f and when we get this g, we will put them next to each other, write them next to each other and say that's our u. That will solve the wire, the string vibration, alright? And the initial condition, okay, and the bound condition need to be transferred also to the f, not just to the u. So we have two bound conditions, u of 0 and t and u of L and t. Remember, we are holding the wire from both sides. So if u 0 and t equal to 0, that means f of 0 and g of t is 0. So this cannot, the fact that f times g equals 0 doesn't mean that g is 0. If g of t equals 0, that means that g at any t is 0. That means that u is 0. Right? Because u is f times g. So that's the trivial solution. We are not interested. Right? So it must be that f of 0 is 0. So we move the bound condition from the u to the f. And the other bound condition also for the same reason. F of L is 0. That means, sorry, u of L and any t is 0. That also transfers to f of L is 0. So the f that will satisfy this equation are subjected to those two boundary conditions. Right? So here is the solution. So here is the ordinary differential equation we are solving. We can solve this by hand. By the way, we also in chapter 21 we will see numerical solution for ordinary differential equation. Some ordinary differential equation you cannot solve them by hand. Okay? Because they are nonlinear. Right? Nonlinear mean f double prime minus f prime f. Or f3, it's not the f3 that's the problem, f3 prime that's okay, but it's minus f squared time just the fact that it's f squared, that make it nonlinear. So for those guys we will basically solve them numerically, but this we can do it by hand, right? So what is k? So k can be plus, it could be 0, could be plus, could be minus, alright? Because over here, remember when we did that step, we just said that it has to be constant. But is that constant is plus or minus or zero? We don't know. Right. We made it, right? We wrote this k because we said if something function of t always equal to something function of x, no matter what you play with the x and t and they are always the same, both of them should be equal then to a constant. That could be minus 7 or 7. Very good. So he's trying the three cases, and when it's 0, when it's positive, you will figure out that this will lead to a trivial solution. F will end up being 0. Why? Because the boundary condition. So for example, if k equals 0, what does this mean? It means f double prime equals 0. What's the solution for that? First f prime is equal to a constant a, and then you integrate one more time and it becomes f equal a x plus b. Right? That's how you integrate f double prime equals 0. First f prime, if you don't remember this, go back again and remember your calculus. So f prime is a, and then f is ax plus b. Here is the solution. What's the bound condition? 0 when it's 0, 0 when it's L. You try to do this and you get a and b 0. So f of 0. So what? So then now u will be always 0 if f is 0. Remember, u is f times g. We cannot allow f to be 0 or g to be 0. If either one of them, no, this need to be function of x and this guy need to be function of t. Otherwise the solution will always, the wire will not move. Okay? So that's a trivial solution not accepted. The second, k is plus. So let's call it mu square. See how he's going to make it minus? He'll call it minus something square. So if it's positive, it's plus. The solution, and we did this, that's the problem we solved before. Okay? When it was positive. So f minus 7f or whatever, you know, but k is positive. So the solution would be a to power e mu x plus b e to minus mu x. And if you don't believe me, differentiate this twice, you will end up satisfying this equation. Alright? So anyway, that is the solution. And so now satisfying the boundary condition, simply saying x equals 0, e to power 0. E to power 0 is 1 plus e to minus 0, 1. So it's a plus b. So a plus b equals 0, and when you do it at L, a plus b e to minus mu L is 0. So how could a and b a and b multiplied by e to minus mu L equals 0? It must be that, well, e to minus mu L is not going to be 0, right? So it must be that a and b is 0. That make the solution also 0. That make the whole u go to 0. This is trivial. The only possible way is k is negative, minus b square. Right? This will, or basically, if you put k here minus b square, minus p square, then this is the equation that you are solving. And so this one is different. Sorry. Well, we can just look here. This one is different from this. This have this solution, but this guy had this solution. When you see f squared plus a constant f equals 0, the solution is cosine plus sine. Why? Well, again, differentiate twice. You will end up with this. If you differentiate this with respect to x, you know the cosine will end up making minus sine, and the sine will make cosine, and then you differentiate again. Alright? So here is the solution for any a and b. Well, now how are we going to get our a and b? Boundary condition. F of 0 should be 0. So when x is 0 and cosine 0, that's 1, sine 0, that's 0. So f of 0 should be basically just a. So 0 equal a. Perfect. Let's cancel this. There is no a. There is only b. Let's do the other boundary condition. F of L is 0. So when it's sine PL, that should be 0. B sine PL is 0. Why? It cannot be that b is 0. If p is 0 and a is 0, we are done. There is no solution, there is no u, there is no movement. So it must be that the sine is 0. When the sine becomes 0, Well, if PL is,
Zero. That's the truth.
or, so PL cannot be 0, because if PL is 0, it's not because of L, it's the P, and P cannot be 0 because we already solved this problem before. This doesn't work. So it must be that PL is not 0. PL must be, or, right, n pi. N pi will do it for us. So it could be 1 or 2, or so PL must be n pi, right? Or P really, because that's what we are solving for. The P should be n pi over L, right? So the B square should be n pi over L square, all right? And so, and how about the P? Well, how about the B? The B actually anything can do, can work, right? So let's take B1. It will still satisfy this. Those are the bound conditions we are trying to satisfy. So with that P and any B, we will get it, right? So take B1, that will become your fx. You are done. Here's your fx n pi over lx, right? And that k was basically, why do we need the k? Well, it's the, why do we need the k? We are done with the fx. Why we care about the k? Right, because remember the k we'll get from here, it's the same k that's here. Remember, those two guys are supposed to be equal to k. So you take that k and you plug it in this equation. Here it is, right? That k, which is p squared, that's here. So now this equation, g plus those guys equal g. You are trying, it's a lot of numbers. Let's just call it lambda. All those guys, let's call them lambda. So this equation, does this remind you of something? This one, f double prime plus p square f, and we said the solution is like this. How about this one, g double dot plus lambda square g? Does this, it's almost the same, right? So the solution should be also some kind of cosine and sine. So I'm calling them not the original b, it's like just different b, right? Notice that this can be done for different n. The solution from the first one didn't say n is 1, say n can be 1 or 2 or 3, right? So then this equation is not, can be done or has to be done for different n. So g of n of t is basically, that's the solution for g of n. And how I'm going to get the value of those exact value of bn and bn star? I got my lambda n. My lambda n is here. But what is my pn? From boundary condition. Or basically when it comes to the t, it's the initial condition. So here is basically the u, it's g times the f. So here is the u. This is the g times the f, right? The g still have the constant in it. We will get them. Lambda, those are basically those guys. And n is 1 and 2, right? So how we can get those bn, initial condition, right? So depending on how you're gonna stack it, basically, you're gonna pull it from the middle and leave it, or you're gonna do this, or you're gonna, right? But anyway, so the solution basically is a general solution for the general equation, general solution for the equation for different n, and those pn and bn star, we will get them from the initial condition. And he's basically saying that this shape, all right, this shape will kill the solution at when this is equal to 0. When the sign is 0, the u will be 0, no matter what is the time. That's the definition of a node. So no matter what is the time, 1 second, 10 seconds, some points, because of this, all the time will be fixed, right? And where are those points? When n by x over L give you a 0, or make the sign is 0, right? So when this sign is 0, and that will happen in x equal L over n, or 2L over n, or n minus 1 over n, those will basically be the nodes. So for depending on how many n you have, and those n will come from the initial conditions, you could end up with basically one node, multiple nodes, alright? So that's basically this shape. So this will basically be n1, he will just go up and down like this, and n2 and n3 and n4, alright? So in music, this will basically be the harmonics. This will give you the main fundamental, and this will give you the different tones on the, and so then you can figure out that the frequency of the noise or the music will really depend on the length of the wire. And so that explained then why the double bass is different from the rival, right? One of my really dear friends was playing this. It's like really, he had a PhD on this actually. He finished his PhD in the School of Music. And so, I mean, it's amazing how big the thing is. But you know now why, right? Because I mean, they want to make those really different frequencies. Okay? So he basically saying that you can change the frequency by changing the lambda or the C, but eventually the wire and the tension, you can tune the tension, and that will change the C. You can make it super, you know, under so high tension or lower tension, but eventually you will just have to go to a bigger length to move to different frequencies. And so that's why the double bass is much bigger than that. Right? So again, here is the solution, general solution, and those guys need to come, Pn and Pn star, come from the initial displacement. Right? So you will get an f of x initially. Is it a triangular? Is it a square? Is it what? And then what? This should be equal initially to the initial function, right? This is the solution everywhere should be equal to the initial distribution. So my initial distribution f of x, right, should be equal to this. Does this remind you of something? Right, Fourier, that's what they have been doing in Fourier series. So basically the solution for the wave equation is to find out the Bn for that f of x. You find the Fourier series, you just plug them in here, and you are done. That's the solution of the wave equation. Alright? And so he's basically telling us here is the Bn. It's exactly the Fourier sine series part. Not from 0 to pi, from 0 to L, because the period is the L of the wire, not pi. Not pi, okay? And sometimes the initial condition is partial U, partial T. Alright? So that's another way that he can give you, like initially we push the wire, or we give him that initial velocity. So if that's the case, you should basically say, well, what is partial U, partial T initially? Alright? So he's just basically differentiating the sine and the cosine. That's why you see the lambda coming out. Because when you differentiate the sine, the stuff inside the sine would come out. Alright? And so again, well, it looked like the Fourier series, but not really, because I mean, you just had the constant is different. It has B and time the lambda. Alright? So it's B times the lambda. The B times the lambda is the Fourier X series, the Fourier sine series. Alright? Very good. So I'm just writing it bigger for you. So again, here is the function, okay? And here is the Bn and the B star of n. This will come from the initial function, and this will come from the initial velocity. So if you start from rest, the ut is 0. Initially, he doesn't have initial velocity. We just hold like this, kept stagnant, and then left it from rest. Well, those guys will disappear because G is 0. Right? If you start when the wire is fixed, but you just give him initial impulse, you just something hit him. You will basically have this guy. I hope you get it. right? And we need this actually for today too. So remember, the sine multiplied by the cosine is basically half sine x minus y plus sine x minus y. We'll do this in a second. You can skip this. So once he put his hand on the ux of t, basically he can basically say, well, here's my solution. It's the b. This is the Fourier expansion times the sine. Remember, let's go back again. So there was b cosine times the sine, and we get those pn by doing the Fourier transformation for f of x, just like what you were trying to do this today in this quiz, right? You had the f of x and you were trying to do that integration. That's exactly what you were trying to do. So once you had your bn multiplied by cosine times the sine, that's the u. All right? So you kind of are done right now, right? But he is basically trying to see how this is kind of like two waves moving across each other, and that's why they create this node. But that's not really super important. But in order to do this, in order to split this cosine sine in two waves, he basically depends on this identity, that cosine times cosine is sine plus sine. Sine x minus 1 plus sine x plus 1. And so you go home and you'll see how he's basically splitting this into those two guys. And so the solution is basically as if there are two waves that crossing. The one is moving this way, one the other going the other way. Alright? So let's skip this. You can see for different initial condition what will happen to the wire. In the last 10 minutes, I wanna, because I have to start chapter 21 next time. So let's talk about this. 12.5.5. Modeling the heat flow from a body in space, the heat equation. This is important for heat transfer. Alright? So in heat transfer, basically saying that the flow of heat should scale with the temperature gradient, time a constant. Alright? So of course in heat transfer in this school we use, for the heat flow we use Q, and temperature we say T. It's partial T partial X. Right? Fortunately we use also K, so it's the same conductivity. So the Fourier law is Q equal minus K partial T partial X. Okay. So but anyway, so he's basically saying that that would be the conductivity that will control the heat flow. And eventually when you write you take a certain body, you know, a sphere or a rod, and you could basically consider how much conduction is coming this way, how much conduction going that way. The conduction, the net conduction at the end of the day, basically going from this side minus this side, where it will go. It will get stored here. If you have Q by conduction coming in and not that much leaving, the difference between them will get stored in. It gets stored in terms of internal energy. It will take this, make this guy hotter, right? So writing the first law of thermodynamics, mass time, basically how much energy, internal energy you have, equal to the net basically change of the, or the net heat flux going in, will results exactly in this. Alright? So I said mass, so you should see basically rho. Well, here is rho. This is, so it's when you put the conductivity over rho and the specific heat, sigma is specific heat. Of course in thermo you probably have seen a CP, but because this is a mass textbook they just use anything they want, so they use sigma. But I mean, it should be rho CP, okay? So what is K over rho CP? That's the thermal diffusivity, that's alpha, alright? So this actually should be alpha. And so partial U partial T is alpha partial second order of U. That takes me back again to what I started with in the class. I told you that eventually we have an unsteady term equal to a diffusion term, and the diffusion could be the viscosity, kinetic viscosity could be the thermal diffusivity. So here's another example where this equation show up again in this form. So the diffusion term, that's because of the conduction is diffusing. How quickly will the conduction, you know, if I put my hand and this is really hot, how quickly does the heat diffuse? It's the thermal diffusivity. Okay? If this was momentum equation, it's the viscosity. That's how quickly does it diffuse. Thermal momentum diffusivity or kinematic viscosity, basically. So anyway, that's the way the equation will look like. And that symbol mean the second order. That's the Laplacian basically of u. When I make this thing, it means partial 2 partial x squared plus partial 2 partial y squared plus partial 2 partial c squared. So they write the equation like this because they save space by. But you know it's 3 term, not just 1 term. Alright? So that's the diffusion term, and not just of temperature. This will be the diffusion of also concentration of any species that you are releasing. Of course, how quick it will diffuse, that coefficient will determine the diffusivity. Alright? So how do they solve this equation? Okay, so this equation, it's not just for us in heat transfer, but in different field as well. Right? So it's a famous equation basically. And so here is his, first he will solve it in 1D. So a really long wire to the extent that the heat basically just mainly move in 1D. Long wire, and you're holding the two sides, maybe this guy with a torch, and you want to heat this guy, and you're wondering how hot and how quickly will it take before you cannot hold it anymore. Right? You are soldering or something. Okay, and you're putting your torch here, and the temperature here instantaneously is like whatever 500 degrees C, and you're wondering, you know, how long before you just have to drop it because it just become too hot. So the temperature profile in here, U is now U is not displacement, U is temperature. The U is function of T and X. At different location, different time, this wire will get hotter or colder, right? And we want to get the solution, U as function of T and X. So he will do exactly the same trick like before. Alright? Look at this. The solution will be a little bit different because this is not a wave equation. Alright? But he basically do the same trick. He basically split the U into f of x and g of t. And he move all the g together, all the f together. And then he say, well, if this equal to this, no matter the x and the t, it must be that both of them are equal to a k, constant. Alright? And you say, well, k is 0, that's trivial. K greater than 0, that's also trivial. So the only way is negative. We did this. All this is equal exactly the same procedure like before. Alright? So it must be basically minus p squared. And so here is the two ordinary differential equation that we will solve. Alright? And here is the solution again, a cosine plus b sine. Here is two initial condition. So he got u of 0 equals 0 and u of L is 0. So how is that possible? Well, it's imagine the wire is putting basically here at room temperature and room temperature, and you're just basically maybe initially you give him he was hot in the middle, or you basically you started with a very hot wire from the middle, or the whole wire was hot and you suddenly tried to put the two sides in ice. The point is the boundary condition is fixed, whether it's fixed at 0 all the time or they are fixed at a higher temperature all the time. Okay, like hot and hot. So using the two boundary condition, he will be able to put basically his hand on the sine PL like we did before and get the n, and now he got his f of n, and he will take this and we'll try to solve for the g. And well, here is his, now the g is a little bit different because of the lambda, so it's basically it's e to minus lambda square. Okay, not like the previous one where also the g end up being a plus b cosine, a sine plus b cosine. Now it's basically just e to power minus lambda. And I'll let you read the rest at home. Thank you.